Next, we're going to look at how to analyze a factorial design. The aforementioned benefits of factorial design, that is, greater efficiency and the ability to study interaction effects, only apply if we use the correct statistical approaches. So let's remind ourselves of our two scientific questions. Is the COVID-19 vaccine effective? And does efficacy differ by sex? How should we approach the analysis of this data? Well, no matter what you're doing, it's always good practice to first plot your data or to get a sense of the values in some other way. This is for a number of reasons, including making sure that the values you have are on the correct scale, that there are no typos in your factor labels, and so on. And I cannot really stress enough how much time and anguish this can sometimes save you. The second step now is to think about your statistical tools, and indeed getting a sense of the structure of the data can help you figure out what type of statistics to employ. However, it's very important to be wary about testing any hypotheses suggested to you by looking at the values of the numbers themselves, as this can lead to incorrect inference, and there's more about this if you're interested at the link on the slide. So let's look at the possible ways we can analyze this data set. You might think, I have vaccine, I have control, maybe I should employ a t-test, one for males and one for females. Now, statistical software will happily let you do this. If we do this, we might come up with a significant p-value for males and a non-significant p-value for females, for example, if you're using an alpha rejection level of 0.05. But just because it's possible to do this doesn't mean that it's the correct way of doing it. So this is not the way to do this for two primary reasons. The first, remember, one of our two questions was about the interaction between sex and vaccination. Doing two separate t-tests doesn't allow us to look at this effect. Although we found p less than 0.05 in males and greater than 0.05 in females, this does not mean that the vaccine is effective in males and not effective in females. Conceptually, we also need to consider one of the key assumptions of hypothesis testing is that independent statistical tests should arise from independent data. Because we used a factorial design where the vaccine was applied to both males and females at the same time, these data are no longer independent. And running two separate t-tests increases our chance of spuriously rejecting a null hypothesis, which is a so-called type 1 error. Instead, it's better to use a two-way ANOVA with interaction. Why? Well, this lets us estimate both the main effects of the model, that is sex and vaccination, by themselves, but it also lets us directly estimate the interaction effect between these two factors. Furthermore, this approach gives us more statistical power. That is to say, we've got a greater chance of correctly rejecting a false null hypothesis by using this approach. I think we'll come to the concept of power more in a later session, but essentially this is the concept that relates to factorial designs being more efficient. Thus, we can look at our ANOVA table and conclude a few things from these data. One, there's an overall significant effect of vaccination on COVID-19 severity, which is a good thing. It means the vaccine works. There's also an overall significant effect of sex, which we might have expected a priori given what we already know about how COVID-19 affects males worse than females. But finally, we don't see a significant interaction effect between vaccination and sex, meaning that the vaccine should be expected to work as well in males and females. On this slide, I'm providing you an example of some R codes so that you can try these statistical tests for yourself. And I also show you how to quickly generate an interaction plot as indicated on the bottom of the screen, which can quickly show you how these two main effects of sex and vaccination interact. Now, as useful as factorial experimental designs are, many practicing scientists actually tend to analyze these incorrectly. So if you had some trouble understanding the whole point about ANOVA versus t-test, you're not alone. In a meta-analysis of neuroscience papers, which was conducted by Neuenhuis et al., roughly 30% of the papers they found in their search out of 513 studies used a factorial design. But really, only half of these 30% were analyzing this design correctly. Now, there are many ways in which you can analyze such a design incorrectly, many more ways than we've actually covered here. So if you're interested in an expanded discussion on all the ways it would go wrong, I do suggest reading this paper, which is linked in this slide. Now, a quick summary about factorial designs. They are used to analyze the effect of two or more explanatory variables on a response variable of interest. They're more efficient than one factor at a time experiments. They can be used to look at interactions between different explanatory variables. And finally, they need to be analyzed with an appropriate statistical model, and that's usually ANOVA or some non-parametric equivalent, not with t-tests.